Good afternoon, Isabella. Good afternoon. Good afternoon, Melissa. Hello, Rachel. You guys are so fast. It's awesome. Hello, Aliyah. Good afternoon, Cynthia. And whoops, sorry. Okay. Right here. Wait, what's happening? Sorry. Uh, what is happening? Hello, Amanda. Awesome. Wait, I'm still getting sorry. What is happening? Hey, Ardell. Hello. Okay, good afternoon, Cynthia. Sorry if I didn't say that. Maybe I did. Hello, Aaliyah, if I didn't say that. Good afternoon, Isabella. Okay, sorry, I'm catching up here. This is happening. This is happening. This is. Okay, yes, that's happening. I'm forgetting something. Pardon me. Okay, almost there. Okay. Hello. Oh, good afternoon, Miles. Good afternoon. I think I said Melissa. Okay. So we are going to get, I still owe you guys. You don't owe me anything. There's no new homework or anything like that. Ball's in my court. I'm still, if you can keep the game things going, that would be good. But there's nothing else, but I owe you, not the other way around. And I apologize. We want to finish deriving the so-called wave equation today. And that's what we're going to do. And I don't really know why I'm stalling exactly. Because I knew people were coming. That's why. All right, hang on. Okay. So one thing I'm going to ask, so we're going to get right back to where we were Monday. Monday, we were spending a lot of time setting up the ingredients for this somewhat large and definitely important derivation / proof of this thing called the one-dimensional wave equation. So Monday we were setting up all the ingredients, the key, the physics ingredients and the math ingredients. The key to this whole thing still is that diagram that I put in the stream. Please have that out in front. I have it too, but I can't. I have a hard enough time managing one screen, so people are here. So I'm going to be doing this is definitely like a note-taking kind of day for sure. We, based on what happened in the other class, we most certainly should get to the end of this thing today, but we'll get right to the end of it. And that's about as far as we'll get. There will be a lot to write down. But if you can have that diagram to your side to reference while you're doing this, that's best. And for what it's worth, also, I'm going to, we're going to take notes in the same sort of packet as yesterday. So let me just remind you where we left off. Again, we're looking at a long, tight string that's tied at two ends of what we're going to call the x-axis. So its equilibrium orientation is horizontal, so to speak. And then someone comes along and plucks the string. That means they take a very small segment of the string and they subject that segment to a very small angular displacement. And that small angular displacement to which they subject it lasts for a very small amount of time, right? And then they let it go. And then it starts that little bit of curvature or distortion in the string that they imposed starts restoring itself by virtue of the string's tension. And what we're going to look at what we are looking at is exactly what happens when the tension in the string uh, starts bringing the string back to a horizontal orientation. That's what we're looking at. So one thing, so we were setting up all the math and physics ingredients. One thing, I was reminding you, is that we still believe in the small angle approximation. It's still true exclusively when we're measuring angles in radians, and the fewer the radians we're dealing with, the smaller the angle we're dealing with, the more true it is. Okay, we said that. And then I just want to remind you this. So this is really where I think we left off. Like I had reminded you, or I was telling you what in principle from the past, which is that if you have any kind of variable, call it z, the difference between two values of that variable we call delta, as long as the difference between the two values, as small as it might be, is finite and measurable, we call it delta. Once the difference between two values becomes so small that it becomes arbitrarily small, or say immeasurably small, like bigger than zero, so it still exists, but smaller than any measuring thresholds that any of our instruments have, then we call it D rather than delta, right? So dz really means delta z in the limit as it approaches zero. Then, and that in principle we knew, so the derivative dy over dx is really a ratio of differentials, right? A derivative dy dx is really just a slope, delta y over delta x, but taken to the limit as x approaches zero. That's what this definition of the derivative really means, right? I'm just reminding you again. And part of what I'm trying to say there is that a derivative is really a ratio of differentials. I'm trying to emphasize that each piece of the derivative is itself meaningful. Like dy is meaningful on its own, even without dx, and dx is meaningful on its own, even without dy. dy is an infinitesimal rise, and dx is an infinitesimal run, right? Put one over the other, and you have an infinitesimal slope, which we call a derivative. Okay, again, I know you know that, and I know we said it yesterday. Then we introduced this new thing, this new symbol, which looks like a backwards 6, and we called it partial. And we're saying that is the infinitesimal rise or run in some function in cases where we have a function of more than one variable, right? And again, I know I said this yesterday, but then we're almost up to like the new stuff. The reason we have to introduce this idea, the reason I have to now say, what if we have a function of more than one variable? And I have to really say it like that, and I have to make a big deal of it because it is not only possibly, but in fact necessarily the case that every bit of math and every bit we've ever done till now has always assumed some kind of cause and some kind of effect. The reason every single experiment you've ever done in a science class immediately collapses into a graph is because every experiment by design is supposed to be us tweaking some knob that we're interested in, like changing some variable, changing the mass of some object, and then progressively, steadily on, at equal intervals, or like rolling a cart down a ramp and measuring where it is on that ramp at equal time intervals or something. We're always tweaking one knob, which we think of as the independent variable, or we might even think in the back of our minds as some kind of cause. And then we're always watching how nature responds in some other knob, how nature turns some knob in response to that, which we call an effect or a dependent variable. And the whole idea is that we hold everything else constant when we're doing that. That's the idea behind an experiment. And that's the idea behind all the math that you've ever done to this point, is you always assume one independent variable and one dependent variable, like y equals a function of x. But, and so, sorry, just, wait, sorry. Right, and so up until now, even if it seems redundant to say, as long as dy over dx equals by definition dy over dx, we might not have had any need to say it up until now, but we could have said, pardon me, all along, like this thing that's, again, I'm sort of reviewing where we were on Monday, but I'm sort of catching us up. Just want to emphasize it again. Like this thing, this equation in the middle of the page that's circled in red, dy equals dy dx times dx. Like it seems like it's just like obvious, or it seems like it's not saying anything new, but it's just a new perspective on an old thing. It's saying it's basically, well, it's saying if you look at any graph and you want to know the infinitesimal rise at any section of that graph, one way you could find the infinitesimal rise is look at the infinitesimal run and multiply by derivative. I mean, rise equals slope times run is all we're saying here, right? But now I'm saying, okay, what if we have a function of more than one variable? Then that would mean that the graph is rising as a result of two factors. In other words, it would mean either that the phenomenon you're looking at would require two different graphs in order to understand it. Oh, like lab 3. Or it would mean if you had really cool techniques or like computer graphics or like a big diorama and like a kindergartner teacher or something like that, it would mean like lab 3. In other words, what I'm saying lab 3, where you took a long string or the simulation of a string and you shook one end and ripples are going back and forth and stuff. Remember in lab 3, if anybody walks in and says, hey, how high is the string? You would have to say, well, when are you asking that question? And also, where are you at? Like, where do you want to know how high the string is? Because it's high over here and it's low over here and it's high over here and it's low. And also, like, when are you asking that? Because each part of the string is going up, down, up, down, up, down, right? So the height of the string is dependent on moment in time and position in horizontal space. Once you specify those two, you'll know you'll have a unique answer to your question, right? So y depends on x and y independently depends on t in the case of, say, lab 3, which is why the most realistic, most straightforward thing to do is make two independent graphs. Again, this is what you did in lab 3, or even before you make the graphs, you took data independently in lab 3. You, on the one hand, you took a whole movie of the graph shaking up and down, or I mean of the string shaking up and down, but like you then analyze that movie two different ways. In one part of your brain, you take one frame of the movie, i.e., you pick one moment in time, and in effect, you hold that constant, right? You pick one moment of time, and now you have a photograph that's giving you y as a function of x, right? Like in any photograph of, again, lab 3, or any freeze frame of your string in lab 3, what you literally are seeing is how the height of the string varies as a function of horizontal coordinate of the string. But you also, and that was like totally valid, and you saw that function while all in one photograph, i.e., time did pass in reality when the string was shaking, but you freeze time for a minute and you just focus on one x value. In other words, you hold x constant in your mind. It's like doing a mini experiment on the experiment. You hold everything else in the universe constant and you just look at, oh, as my eye tracks from left to right on this string, I see that nature has brought the string to different heights, right? So you independently think of a y x graph. Again, this is lab 3, and you can independently look at slopes on that graph and derivatives, and you can see that as your eye traces from left to right, the height changes. And if your eye were to trace left to right infinitesimally, you would see infinitesimal gains or losses in the height, right? But also, even though that's all true, at the same time that's true, you have this other graph or this other set of data that you took from the same phenomenon, right? It's all one big phenomenon of a pulse going down a string, but you gathered a different set of data from there, and and what you did there was you picked one little slice of the string, one arbitrarily or conveniently chosen x coordinate, and you took a movie, or you looked at the movie there just at one x coordinate, and you watched how the string went up and down as a function of time, like because now it's a movie, not a snapshot. So you held x constant and you made a graph of y as a function of time, and yay, it turned out to be also a cosine graph, just like the other thing. And that cosine graph, you could take slopes and derivatives and whatnot, meaning that the infinitesimal increase in y was totally depending on any infinitesimal increase in time on that graph. So that's what this statement down at the bottom is saying, look, if we believe superposition, if we believe that the X action and the time action are both happening at the same time, but happening independently, such that we can separate them out and make two separate graphs, then really, if anybody wants to know at any moment how much has the string risen in some, what's the infinitesimal rise in the string? Well, what it is, again, I'm just trying to explain the last line on this page here, the last line in brown. I'm saying any infinitesimal rise in string, the total amount of rise in the string, like the total differential, is a sum of the rate at which it rises per x times x plus the rate at which it rises per time times time. This is just, in other words, this down here, oops, sorry. This equation down here is just the expansion of the equation above, the application of the equation above into a multivariate function scenario. And the reason we are now looking at multifunction scenarios, the reason we're now looking at multivariate functions is because that's what nature is presenting to us. I'm not assuming we've ever done this in math before. I'm saying this is the math that we're now doing. Just like at the beginning of the semester, Hooke's law just presented us with a differential equation. So we have to, dig up whatever tools we can to solve that differential equation here for the first time. And it is the first time in all of science. I mean, unless you happen to have taken like other courses that you do not have to have taken, it's the first time in science or in math we are presented with one variable depending on more than one independent variable. And as long as we still believe in Galileo, as long as we still believe that each axis exists independently but simultaneously with every other axis in nature, as long as we believe that the laws of physics hold constant and true in every frame of reference or every coordinate system or every coordinate axis, and finally, as long as we believe that the whole is equal to the sum of its parts, then we're not going to have any difficulty doing this. We're going to, from now on, we're going to, yeah. So, okay, now for anybody who's tracking this, I'm now into the new, like, here we are today. That was technically like the recap of yesterday, of Monday. But now I'm saying, okay, given all of that, in our analysis of any pluck or any pulse on a wave, we have to now recognize y is a function of two in the very least, in a one-dimensional case, at least, even if we have just a one-dimensional string, y is going to be a function of both x and t. At a minimum, y is a function of two variables. So that means now, if we're interested in derivatives at all, which physicists always are, if we're going to be taking derivatives of any kind, we're going to be careful from here on in to make sure that whenever we take a derivative of y, we're careful to specify, do we mean y, the derivative of y as it depends on x, or the derivative of y as it depends on t? Each one of those separate piece derivatives we call a partial derivative. If we ever need the whole derivative, we'll add them together and get the whole. But from here on in, there's no such thing as just a derivative. It's the derivative of y with respect, well, really, from here on in, it's either the partial derivative of y with respect to t, or it's the partial derivative of y with respect to x. Like, that's what we're focusing on now. And in order to make that super clear, we use this new symbol, which is neither a capital delta triangle nor a lowercase d. It's now this backwards 6 thing, which we just literally call partial. I mean, that's it. Okay. So that's what all that means. We're just about ready to go now, finally, with the proof. Oh yeah. Okay. So now we are ready to go with the proof. Like all that was like a whole day of the background underlying assumptions from math and the background underlying assumptions from physics that we're making in order to go in now and look at that picture. Oh yeah, okay. So look at that picture, please, please, please. Look at that picture I gave you Monday, or that's in the Google stream. And notice now, we're going to analyze it, but notice that what that picture is, it's very, very similar to or analogous to any one given frame that you excerpted for analysis purposes in lab 3, in that picture is a piece of our string superimposed on a y-x coordinate grid, right? So it's literally a photograph. It's like one moment in time that's showing us how y is depending on x for that string. But what we're going to analyze now is what's going to happen in the next moment in time, or the next moment. Like that string, if we let it go now, it's going to like presumably pull itself back to flat. And so we're going to analyze the dynamics of that string. I can't draw them into that picture because the picture's static, But we are now assuming that that string, that's the y as a function of x frame excerpted from a larger y equals function of x and t, for whatever that's worth. So now what we're going to do is apply Newton's second law to the string. Like we come over, we plucked it, we let it go. So we're not touching it anymore. So we're going to look at the only force, and we're not worrying about gravity. We don't, first of all, this whole thing's going to happen to you. The string is too light to be worried about gravity. Also, the string could be a cello string if we want, and gravity totally wouldn't matter. So there's no gravity, there's no external forces on this string. The only thing that's going to be acting on the string is the two forces of tension at either end point of the segment that we're looking at. Like, in other words, the two red arrows in your picture. They are, one's sort of pulling up and to the right, the other's pulling down and to the left. If they were perfectly equal, they would perfectly balance each other out and the string wouldn't do anything, but they're definitely not perfectly equal. I mean, their magnitudes are equal, but overall as forces, they're not equal because the angles are not the same, because if the angles were, the string wouldn't be curved. So we're ultimately going to look at the net force of tension acting on the string. So I'm doing F net equals MA, like that's my first line in blue, F net equals MA. F net equals MA is a vector equation. In and of itself, it means that it simultaneously yet independently acts or is true on every axis. Like, right, it's independently true on the x-axis and it's independently true on the y-axis. So just like we always used to do in physics 1, I'm going to just analyze each axis independently. And just like we did in physics 1 or physics 203 or whatever, I'm going to first look at the axis that I don't care as much about. Like, I really think that the activity here is going to be in the y-axis, like the string is like bent like this. Well, anyway, I think the ultimate activity is going to be in the y-axis. I'm going to look at the x-axis first. That's always my habit. Always look at the thing that I'm ultimately interested in last, because I might pick up information from other axes along the way. There might be simultaneous equations or something like that. Or also, I can make sure I know what I'm doing with the other axes before I do. So I'm going to look at the x-axis first. The x-axis, net horizontal force equals mass times horizontal acceleration. Like, that's what I'm saying here. So I zoom in on the two tension forces. I mean, there's two tension forces, one over here pulling down and left. They're both from the string itself, but one over here pulling up and right. I zoom in on them. I divide them into components like we always do in physics. So we got a horizontal component of tension. I should say, sorry, just to be clear. Like this right here is T2x, so to speak. This right here is T1x, et cetera, et cetera. Okay, so I've just divided them into components. So now I'm going to look at the x-axis. Oh my God. What? Oh, okay. I'm going to look at the x-axis first. Okay, so. Okay, so I'm looking at the x-axis top line on this page, the line in brown, and I'm saying, okay, I've got two horizontal components of tension, both acting on the string. The sum of them is the net force, but they're acting in opposite directions. Like I should have, assume to the right is positive and to the left is negative. Not that it matters. So it's the right-hand one minus the left-hand, where they're acting in opposite directions. So T2 cosine theta 2 minus T1 cosine theta 1. So all of that together equals delta M A sub x, like the horizontal net force equals the mass times the horizontal acceleration. Also, remember, I'm saying delta M because we're not just looking at some little point on the string. We're looking at a segment. We're looking at a little interval or length, hence why I'm calling it delta M. Okay, okay. All right. But now here's the deal. I'm starting with the x-axis first because in a way it's the easier, more straightforward one. The x-axis by definition is the equilibrium axis. That is to say, this long string is being held fixed at two ends by you and your lab partner, or it's pegged into the wall with two nails or something. So we absolutely do not ever expect or believe that the string is going to accelerate back or forth in the x-axis. No way. It's bound along the x-axis. So I know that the acceleration along the x-axis is nothing. By definition of the x-axis is the equilibrium axis. Therefore, the red line, I say, okay, fine, then the two horizontal components must be balancing each other out. And that is true. That's a fair assumption. And that's all I learned from the x-axis. It's almost just like a check. I mean, it turns out there's not that much interesting to learn from it, but it's almost like a check, or it's just a, okay, this is how we set up the procedure. That makes sense to me. I'm saying if I'm doing this, therefore, I believe that my procedure for analyzing the axes is correct. Now I'm going to use that procedure to go to where the action is along the y-axis. I say the action because the string right now is bent out of shape in a y kind of way. It's going to have to fall down or fall up or whatever to get flattened out in the x-axis. So it's going to that little segment is going to accelerate back down. Let's look at that. That's the action I want to look at. So the y-axis, I say something similar, t2 sine theta 2 minus t1 sine theta 1. And, they're in opposite directions again because one's going up and one's going down. So that equals delta m a sub y. But now, and by the way, I'm sort of talking fast because I'm sort of excited and everything, but we're not, and I do definitely want to finish this today, but we will. So I won't get off the topic, but please do, I'm not trying to go so fast that you can't ask questions or something. Please do stop me or tell me to go back a page or whatever, whenever you need, whoever you are. But okay. So we have T2 sine, but what we have so far, this is a long proof. We're up to the line that says T2 sine theta 2 equals T1 sine theta 1 equals delta m a sub y. But now, remember, we do have two different forces here ultimately because they have two different directions. Therefore, they're happening at two different angles. Therefore, what's really happening, what we're really ultimately saying is the y components of these tensions, the y components must not be equal, and they're not, because the two angles are different, so the two signs will be slightly different. But that's just it. It's just that the y components are different. The tension itself, the magnitude, must be the same everywhere through the string. That was something we went to pains to remind ourselves on Monday. The tension magnitude, i.e. T2, must equal T1. They're the same by definition of tension. So I'm saying they must be the same, so I'm going to drop the subscripts and just call them T now. Okay, I'm not saying the two forces are equal. They're not equal in direction, and all their components are not equal, but the overall hypotenuse, so the overall magnitude, must be equal. So my next line in the proof is I'm saying T2 must equal T1, therefore let's just call it T. All right, so I go to the next page. So I changed it to T. And again, obviously I've already written this out, and I don't know if that's good or bad for some of you, but just I'm explaining it. You just have to follow me. I mean, some obviously stuff is written before I even say it, but I'm on the first line now. T sine theta 2 minus T sine theta 1 equals delta m a sub y. Okay, so I factored out a T. So now I have that. Now, remember, small angle approximation. These two angles are different, but they're both very, very small, measured in radians. So in each one, wherever I see sine, I can swap out sine and put in theta itself, like sine of theta and theta are essentially interchangeable, or excuse me, they're approximately interchangeable if the angle is really small. And a better way of putting that, especially with the limit notation, is the smaller they are, the more true that approximation is. Okay, so I'm going to sub out the sine and just put in theta, but it is an approximation. So I'm not playing fast and loose. This is like one of my favorite things in physics. Like, I'm using an approximation, but I'm going to precisely admit that I'm using an approximation, kind of like in a lab where you make a measurement. But we all know measurements are all intrinsically uncertain. They always have uncertainty associated with them. So you make a measurement in a lab and then you declare the uncertainty. You say this thing is 5 meters long plus or minus 0.025 meters or whatever. And by adding that uncertainty, you're actually making the whole thing more true, if you know what I'm saying. It actually makes it more precise and sort of almost more certain because you are certainly asserting the exact level to which it's uncertain, right? So what I'm doing here is I'm doing an approximation, but I'm asserting that it's an approximation by changing my equal sign to an approximate equal sign. So there's no lie. So it's not a lie. It's not a fiction. It's strictly true that it isn't strictly true, if that makes any. And I'm making a big point about saying that because in the end of the day, I'm a physicist. I still am going to want an exact equality at the end of the day. But that doesn't mean I can't use an approximation along the way to get there. And that's what's happening here. So right now, we have an approximation, or we have two sides that are approximately equal. And again, remember, like, how approximate are they? Like, I mean, are they wildly off? Well, oops, sorry, someone's going. the two sides of this equation written at the bottom of the page, like T quantity theta 2 minus theta 1 approximately equals delta m a sub y. The smaller the angle is, the more true this statement is, or in other words, the less of an approximation is. And if you went all the way to the limit where theta was nothing, in other words, or put another way, if you went all the way to the limit where the 2 points that we're looking at are so close to each other that it's in fact 1 point, that there's no difference between this theta and that theta. If you went all the way, not literally if you only looked at 1 point, because then nothing's happening, but if you went in the limit as you get arbitrarily close to 1 point, or put another way, if we take these 2 points and get them so close that if we bring the 2 points together, that they're far away enough to not be 1 point, but close enough together that we couldn't possibly measure the difference between the two. Like, this is where limits really mean something in science. If ultimately we look at 2 points that are so far apart that they are in fact 2 points, but so close that they're below the threshold of all of our measuring equipment, then, in other words, so close that even though it's not 0, we can't put a number to what they are. That's what we mean by in the limit as we go to 0, right? So if at the end of this whole proof, if I can do something like that, if at the end of my proof, I can take what I'm saying to the limit, then I will be able to drop the approximation sign and turn it into an exact equality. And that's actually what we will do. And that's a very traditional thing to do in physics, which, by the way, escaped me for years and years. I did not understand that was happening. This is like the first proof I ever saw where that happened, and I didn't understand that's what was happening, and I blah blah blah. But we do it. It's one of the cool things about limits that we can really do that. And again, let me just reinforce that limits, as psychedelic or as obscure and weird as they sound, they really mean something in science, because a limit just means below the threshold of measurement, big enough that we know it exists, but too small to quantify. Like, if you think about it, there really should be a name and a concept for that nether region. It's a very important region. And that's what we're talking about here. All right. So anyway, T quantity theta 2 minus theta 1 approximately equals delta m times a sub y. And by a sub y, I just mean acceleration in the y direction along the y-axis, acceleration of this string segment. Okay. So I'm now going to the next page. Okay. Now, excuse me. All right, so we have T theta 2 minus theta 1, and we equals blah, blah, blah. And we got there by just getting rid of the signs. But now I'm going to say something new. I'm going to say something that we've never said in this class before. I think you'll buy it, but it is new. I'm going to say, if you understand this small angle approximation thing, if you understand we're saying the closer you get to an angle of 0, the less of a distinction there is between the angle itself and the sine of the angle. And you know, I think you can see that on a graph. You can picture it on a graph, like both, you know, one graph is a straight line, like at 45 degrees, and the other is a curve, but they both start off as straight lines that are going up and to the right. Or you could see it on a calculator. Well, I'm saying, however you understand this, that the smaller the angle is, the smaller the smaller the angle is, the more closely it resembles the sine of the angle. Well, then actually, if you remember that tangent is defined to be sine over cosine. And if you remember that the smaller the sine of something is, the bigger the cosine is necessarily, right? Like, as sine goes, like, think of first quadrant angles, the unit circle or whatever. Like, the smaller the y coordinate gets, the bigger the x coordinate gets. Or, you know, sine of 30 degrees is what I think you know that. When sine goes down, cosine goes up. So if you put sine over cosine and you start looking at smaller and smaller angles, the sine is going to get smaller and smaller. The cosine gets bigger and bigger. So the whole fraction is going to be even smaller. So if you believe that at small angles, you can treat theta and sine of theta as kind of interchangeable, then actually it's even more dramatically true that you can treat theta and tangent of theta as essentially interchangeable. There too, you can look at a graph. Think of the graph of tangent of theta, if that helps. Or like, you could just take out a calculator, like literally. So I have a calculator right here just to make the point. Like, I'm in radian mode. None of this makes any sense if you're in degree mode, but I'm in radian mode. So I type into my calculator tangent of 0.01, let's say, and I press return. And so I'm doing the tangent of 0.01 radians. What I get on my calculator is, I'm literally reading out loud, is 0.01000333. Okay, that's, first of all, that's super close to 0.01, right? I put in 0.01 and what I got was 0.010000333. So depending on how many significant digits I'm going, that basically looks the same. But even more to the point, what I just did was I took tangent of 0.01. Let me take an even smaller angle. If I take the tangent of 0.001, now literally what my calculator says is literally 0.001. Like in other words, the next digit is so far out the calculator can't even produce it. So it's basically telling me that they are identical. They're not literally identical. But what I'm saying is the smaller and smaller the angle gets, the more and more the tangent resembles the angle itself, to the point where my calculator can't even pick up the distinction. The tangent of 0.001 is 0.001 according to my calculator. So I'm just saying now we deal with small angle so much of our lives in physics, like the first exam, that you hear a lot about small angle approximation. You can swap out theta for sine. I'm saying actually it's also true that you could swap out for tangent. It just doesn't come up as frequently. Like you haven't heard that up until now because it doesn't come up as early. But there's a lot of other contexts where it does come up. So the first time, so when I saw this in the proof the first time, I had no idea what was going on. And when I finally realized, oh my God, I guess this is just another small angle approximation, then I was pissed. I was like, well, if this is true, I guess it makes sense it's true, but why did no one ever tell me this before? Well, because it didn't matter until now, that's why. But it is true. So now what I'm going to do is this funny thing where I had sines on the left-hand side of this equation. I popped out the sines and put in thetas. Now I'm going to pop those out and put in tangents. It looks like I'm making things more complicated. And in fact, I am temporarily. I'm actually temporarily making this more complicated, but because I have a goal in mind. Just like if you want to remodel your kitchen, you got to make a mess first with construction stuff. Like it's like that. So I've just now made this, I've now changed ultimately all this talk is to say whatever was true about the sines a couple minutes ago, I'm now going to replace them with tangents because I have a goal in mind. Well, really, because I'm plagiarizing Newton, and Newton I'm not plagiarizing, but I got this from Newton, and Newton had a goal in mind. So we now have on the left T quantity tangent theta 2 minus tangent of theta 1 all equals delta M A sub Y. Okay, so again, we're churning it. We're just like rearranging until we can get something out of this. And you can stop me whenever. You can totally stop me, whatever, but I'm going to the next page. All right, so now I just recopied. So on the top of the next page, we have tension. Tension times quantity tangent of theta 2 minus tangent of theta 1 approximately equals delta M A sub Y. Again, that delta M just means it's a chunk of mass rather than a point of mass. And the A sub Y means acceleration along the Y axis. So all of this, we're just doing F net equals MA. In other words, by the way, I should remind you, even though we're analyzing a new kind of situation, like a pulse on a string, this is just old physics technique here. Like this is mechanics technique. It's just F net equals MA. So we're not introducing a new law or anything like that. We're using an old law to analyze a new situation. All right, now I want to talk about those tangents. I put tangents in for a reason. Newton put tangents in for a reason. Let's see what that reason is. Let's zoom in on either of the angles. I'm going to zoom in on theta 2 just because that's the one where things happen to be going up and to the right. It's easier to talk about, but I could zoom in on either one. I could consider either angle. I could consider either tangent. I'm going to consider theta 2. So we'll look at that picture. This is the vertical. Sorry. Right, the horizontal component of the tension is T cos theta, like we said before. And again, I'm just calling them T's now because all the magnitudes are the same. And to the up component T sine theta. Oh, sorry, this is all theta 2. I didn't mean to do that. This is all just an analysis of one of the angles. Well, tangent of theta 2 by definition equals sine over cosine of theta 2. But sine is like opposite over adjacent. No, it isn't. Sine is opposite over hypotenuse, and adjacent. What am I saying? Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So the hypotenuse is canceled in effect, and I'm saying like tangent of theta 2 necessarily is the vertical component of tension over the vertical component, over the horizontal component of tension. But what that approximately equals is the rise in the string over the run in the string. Like, remember, what your picture is a piece of string that's curved. Those two red arrows are tangent lines. Like, those are tangent lines. They represent what the force is doing at those moments. They're called tangent for a reason. But the slope of the tangent line is in the limit. What I'm saying is a derivative is a slope taken to the limit, like I've been saying for an hour and for 2 days, right? I'm saying if that string were literally straight, if that string were on a diagonal right there in this little chunk that we're looking at, if the string were literally on a diagonal, then whatever the tension would be doing would be literally exactly what the string is doing. Like the tension has to point along the string at all times, but this string curves a little bit. So as long as I look at, so of course it, so the average, so the slope of the string does not actually remain constant, right? The slope changes at every point, which is why if we pick any 2 points in the string, the slope of the line connecting those 2 points is like the average rate of change of the string. But if we want the actual exact rate of change, we'd have to take a tangent line and look at any point. I'm ultimately saying here, derivative is approximately equal to slope, right? Derivative is approximately equal to rise over run. It's exactly equal to slope when you go to the limit to 1 point. But so I'm ultimately trying to say, sorry, here, let me do this better. Sorry. This is a better way to say it. I'm saying derivative dy dx is slope delta y over delta x in the limit as delta x approaches 0. So right now we're not in the limit yet. We're like making approximations here. But if you see just in the triangle, basically I'm saying we're looking at tangents here. We're looking at rises over runs because it enables us to instead look at derivatives. It's not a coincidence that the derivative is known as the slope of a line that's called a tangent line. It's not a coincidence that the tangent function, sine over cosine, is a rise over a run. That tangent is opposite over adjacent. You probably have thought this all through yourself in your own way before, but I'm just saying now that tangent of theta 2 is approximately dy over dx. Like it is literally, right? And so I'm going to substitute in dy over dx for those tangents, but I'm going to use those partial symbols because y actually depends on both x and t. So if I want to look at the rate of change of y as a function of x, I have to be careful and use this new symbol that we introduced, the partial symbol. But this tangent is approximately that, partial y with respect to partial x. The partial derivative of y with respect to x is what I can now substitute in for tangent. This is why I went to pains to get rid of those signs and call them tangents instead, because tangent allows us to look at derivatives. The derivative is the slope of the tangent line. Again, they're not exactly the same. This is all an approximation. So I still have the approximate sign in my equation. But the smaller intervals I'm looking at, the more and more this approximation is true, or the less and less it's an approximation. So what I've written here now in this line here is I've taken out the tangents and put in derivatives, but I've written them in kind of a funny way that might look intimidating at first. I'm saying, instead of tangent of theta 2, I'm saying dy dx evaluated at point number 2, at that point that we called x plus delta x. And the other one, tangent of theta 1, I'm saying is dy dx again. It's dy dx, it's slope, derivative, whatever, but over there at that other point, at the first point that we just called x, right? So that dotted vertical line just means evaluated at, just like you might have it when you're doing a definite integral or something like that. Why do I have to be this careful or this picky or whatever? because I have to remind you, and it'll come up later in this proof. Remember that if you have some function, and we do have a function, if we have y equals f of x comma t, we don't know what the function is, but it's a function. And we're looking at one of its graphs right in that picture. When you have a function, if you take the derivative of a function, what you get is a function. Like the derivative of a function is not a number, it's a function. Let me back up and say this even better, or maybe. A function is a box, right? Number in, number out. A function is a rule that you put a number in, you get a number out. An operation like differentiate or integrate or something, an operation is not something you do to a number. An operation is something you do to a function. You get function, you put function in, you get function out. Like when you differentiate a function and you get a new function. If you're looking for a number, well, then you can have mine. It's 472. No, if you're looking for a number, then you have to evaluate that function at a point. Like if you want a value for y, you take your new function and you plug in a particular value of x, and out comes the value of y. So what I'm saying here is these two tangents, that like these rate of changes of the string, like the slope of the string over here. So basically I'm saying we want the slope of the string over here minus the slope of the string over there. So that is dy dx evaluated with this x value, like whatever, I don't know what this function is, but it is a function. If I plugged in x plus delta x over here, I get a number that represents the slope over there. If I plug in just x over here, then I get a different number that represents the slope over there. That's what's going on in notation. Again, please feel free to stop me. But now I'm saying that we have t, so I'm on the second line of this, t quantity, partial y partial x evaluated over here, minus partial y partial x evaluated over there, all approximately equals delta m a sub y. Okay, now I go to the next line. Oh, I guess I just recopied it. All right, so then I just recopied that. For some reason, I wrote it twice. Sorry. Now I'm going to hold. So the left side's looking a little intimidating, maybe, but it's got derivatives. And now I'm going to hold that thought. I'm going to move over to the right side now. The right side says delta m a sub y. Delta m, again, because it's like a little stretch of the string. It's a mass. It's an interval of mass, not one point of mass. And the whole reason I have to be careful about that is I don't know how much mass it is. The longer a stretch of string it is, the more mass it is. In fact, that's the one thing I do know. I know how dense this string is. I know its mass per unit length. We call that, so I'm here now, we call that mu. Mu is the name, and it has nothing to do with friction. Again, for those people who are just tuning in right now, this is a totally different mu. I'm sorry, it's the same letter. It has nothing to do with friction. There is no friction involved in this problem. But mu stands for one-dimensional density, delta m over delta x, like mass per unit length. That's what density is. Therefore, I'm going to say mass equals density times unit length. I mean, if density is mass per length, then mass is density times length. So for the delta m on the right side, I'm substituting in mu times delta x. Okay, that's all I've done. On the very last line of this sheet that you're looking at, I've now substituted in I've substituted in mu delta x for delta m, and I still have a sub y there. That's the last line of the sheet. Now, I'm going to go to the next sheet or the next page, whatever. I'm going to tell you right now what I'm going to do. I want to make sure the time. Oh, we're good. Okay. I'm now going to do two things in one step. It might upset people. I apologize in advance. I'm going to divide both sides by t. And I'm also, in the very same moment, I'm going to divide both sides by mu. Like, please don't kill me. Or not for that reason anyway. So I'm going to divide both sides by t. And again, like I hope everybody would agree that that's like legal. And I hope everybody would agree that every step I'm doing so far is legal. But the fact that I'm allowed to do it, doesn't necessarily tell you why I'm doing it. Why I'm doing these things is because I have a goal in mind. Newton had a goal in mind. Remember that what we're looking at here is the final copy of a proof. Okay, like Newton probably went through a lot of drafts before he got to this final copy. So there's some Monday morning quarterback going on here. But anyway, so if you're as long as you understand that it's okay to divide one side of an equation by t, as long as you divide the other side by the equation by t, then that's all we all have to understand at the moment. If you're thinking, well, why would you possibly ever think to do that? I wouldn't, neither would you. unless I was trying to accomplish something. And you'll see what I'm trying to accomplish when we get there. All right, so I divide both sides by t, and I divide both sides also by mu. So what I have, oh, sorry, I didn't even do that yet. Okay. Well, I'll do that in a minute. I'm sorry, I skipped one. There's something else I'm going to do first. Maybe I should have waited on this. So I recopied at the top. I recopied what I had there. But at the top, I'm focusing. Everything I said is true. I'm just going to do it in a different order. I apologize. At the top, it says a sub y. That means acceleration along the y-axis. Well, remember, acceleration is the derivative of velocity. Velocity is the derivative of position with respect to time. Like, this is a physics concept now. Acceleration is change in velocity per time. And we're talking about acceleration along the y-axis. We're talking about the rate of change of vertical position with respect to time. So what we're talking about here when we say a sub y, we literally mean d2y dt squared. Only the d that we're talking about here is now partial. Because, right, in other words, now time is getting introduced. Now I'm going to acknowledge or embrace the role of time in all of this. Acceleration is second derivative, but it's not just any old second derivative. It's second derivative of position with respect to time. So in principle, we knew this. I'm saying a sub y by definition is partial to y, partial t squared. Partial because it's just the rate at which y changes in time, while in the other side of our brain, we know y is also at the same time changing as a function of x, but that's a different partial rate, which we're invoking on the left side of the equation. Okay, so I'm going to substitute in partial 2y per partial t2, and that's what's happening right here. Okay, on the right side of the equation, all that explanation just to substitute, is just to make the substitution, which I just made illegible. AY, I'm substituting d partial 2y partial t squared. Now that I made that substitution, now I'm going to divide both sides by t, and I'm going to divide both sides by x. I apologize for jumping the gun on that before. Okay, so here we have the top. And again, stop me if you want me to go back or whatever. All right, so now we have a bloody mess on the left. I mean, the left looks intimidating to me, and also looks like messy to me, and I know that. We're going to deal with it. On the right side, but on the right, one of the reasons I divided both sides, well, I divided and stuff. The right side is now a constant over, and please remember also, the variables here are y and x and t. Y is the dependent variable, x is an independent variable, t is an independent variable. Everything else you see is a constant, like mu is the constant density of this string, t is the constant tension in this string. Okay, so they're together. You can even like put them in parentheses if you want. They're on the right side next to this second derivative. It's the left side that's a mess. Well, I don't know. I don't necessarily know how to clean up the left side off the top of my head, but I know this. I know what I said at the beginning of the whole proof, which is that not only is the left side messy, but also what's like a little bit annoying and unsatisfying to me at this point is this, for all this work we're doing, we're only getting an approximate equality. I ultimately don't want that. I want an exact equality. Remember that this approximation becomes more and more true, or less and less of an approximation, as the 2 points get closer and closer together. That is to say, as delta x, which is the difference in x coordinate between these 2 points that we're analyzing, in the limit, as delta x approaches 0, this becomes an exact equality. So what I want to do is actually take this thing to the limit so that I can get rid of the approximate equality and maybe clean it up a bit. Am I allowed to just like take anything to the limit just because I feel like it? Well, no, you can't just take the left side of some equation to the limit just because you feel like it, but you can if you also take the right side to the limit. Like, you can do whatever you want to one side of the equation as long as you do it to both. So that's what I'm going to do. I'm going to take both sides of this equation to the limit as delta x approaches 0, right? And it's getting very sloppy there at the bottom. At the bottom here, it's trying to say take the left side to that limit, and it's also trying to say take the right side to the limit. But in the right side, I just put like a squiggle inside the parentheses because I couldn't fit it anymore. So I apologize. But I'm taking both sides to the limit as delta x approaches 0. Before I go, and I'm going to turn the page obviously in a moment, but one of the reasons I didn't like write out the whole right side is because I ran out of room. But the other reason is, let's look at the right side first. So again, I'm taking both sides of this equation to the limit. One, because I'm allowed to take one side to the limit as long as I take both. And two, I want to, because I want to get an exact equality rather than a approximate equality. So let me focus on the right side first. If you take the right side to the limit as delta x approaches 0, there is no delta x term at all in the right side. It doesn't mean you can't take it to the limit, but it means taking it to the limit is easy, it's trivial. It's like saying, what's the limit as delta x approaches 0 of 5? The answer is 5, right? I mean, that's maybe a stupid example, but you might remember in math, I mean, if there's no issue about delta x, then there's no issue. So I take the right side to the limit because I have to, but what I get is literally the right side. Like it won't affect the right side. Okay, so when I'm going to recopy this on the next page, the right side, it's going to look like I didn't do anything because I did, but nothing happened. So then I'm going to focus on the left side. I hope everybody's with me. In fact, I on purpose don't even want to turn the page yet. And we are actually almost there, really, which is great. Well, yeah, no, okay. Do I want to go? I want to. Yeah, all right. So let's go to the next page. So the left side is this big mess. The limit. Okay, the left side is this limit as delta x approaches 0 of nonsense, well, no, of a derivative evaluated over here minus the same kind of derivative but evaluated over here all over delta x, and that equals some stuff on the right side, a constant over a constant times a second time derivative. Okay, like there's a lot going on. The right side's not going to change anymore. The right side is what it is. But now let's look at this left side. I mean, this left side looks very intimidating. I mean, or to me, it does. And it's like hard to sort out what's going on the left side. But let's back up and remember something. What I said before, when you have a function like let's forget about all the t's and the multivariable everything, like all the time stuff is happening on the right side. But on the left side, all we're dealing with is y and x. So let's just remind ourselves like what happens in functions such as y equals f of x. If y is some function of x and you take the derivative of it, what you get is some new function. You could call it f prime if you like, or you could call it g of x. Let's call it g of x just to make it clear it's totally new, right? If you take the derivative of a function, what you get is a new function. So in fact, yeah, I'm going to add a page here. What I'm saying then, so I'm saying, think of dy dx as a brand new function. We still don't know what it is. We never knew what the original function was. We just know it's a function. So dy dx is the derivative of our old function. It itself is some function. I'm going to call it g of x. If I call it that, and look at this. Right, the right side is still mu over t times times the second partial derivative of y with respect to t. That's the right side. The left side, right, I'm substituting in. I'm saying we had a derivative evaluated over here at x plus delta x, and we have a same derivative evaluated over here at x. Derivative is just some function. So what we have here is the function, and we're calling it g. So we have g of x plus delta x, like g over here, minus g over there, all over delta x. What we really have, in other words, on the left-hand side is this is really what we have so far. We have the rise in g over the run in g taken to the limit as run goes to 0, right? That's what we have here. And by definition, I don't know if you can, however, whichever way I'm writing it, if you go back to page, well, maybe I should pause and ask, does anybody see what, I can make one new substitution now that's fairly phenomenal. Does anybody see what's happening? Like we have the rise in g over the run in g, but taken to the limit as run approaches 0. We have, in effect, the slope of g, but taken to the limit as x equals 0. What is that? Like, or if you look at the definition that I reminded you of at the beginning of this class or on last Monday, like what, put another way, I don't know if anybody wants to say in the chat or anything, but like this whole business here should remind you of something, or looks like something we said at the beginning of this. If it weren't G's, if it were F's, it would look precisely like something you know from the beginning of this class or from Monday or from math class. What is that thing on the left side? It's the definition of something. I'll take any answer from anywhere. I shouldn't put people on the spot, but I kind of need to. Does that, so the thing in red, even if I've totally lost everybody or whatever, which would be a bummer. Even if I've lost you, if you're caught up even in taking the notes, or even if you just tune in out, if you just look at the thing in red, if you just look at it in isolation with no context, does it look like anything to anybody? It's the definition of something. Yeah, like note this. So if you have page 6, note that. And I'm going to go back. I'm being sort of obnoxious, I know, but I didn't mean to make sure that I'm not just totally talking in a vacuum here. This is not supposed to be a put you on the spot thing, but what is slope taken to the limit? What is the slope? Not what's the slope of a tangent line? What is rise over run taken to the limit as run approaches 0? It's a good thing I have such a strong spiritual center right now, because otherwise you would all be seeing a grown man cry right now. What is slope taken to the limit? What is the slope of the tangent line to a curve? What is rise over run taken to the limit as run approaches 0? What is the limit of delta x? I mean, what is that red thing? Okay, how about this? Can anybody affirm that they can hear me right now? I have to change the view so I can even see you, but or have I really lost everybody? Hold on. Okay, thank you, Miles. Totally appreciate it. Thank you, Isabella. Thank you, Bill. Okay, phew, at least we're okay. Okay. Thank you, Isabella. Thank you, Billy. Thank you, Miles. Awesome. Now, so that means I'm asking something that's actually hard. All right. So I say the answer. I'm not trying to shame anybody, but I do want to make sure at least that if I say the answer, it'll land. Like, or at least enough of us are listening now that when I say the answer, you'll understand it's significant. The thing the thing circled in red is the definition of the rhymes with schmerivative. It's the definition of the derivative that. Yeah. Oh, okay, okay. Okay, but I appreciate that. I see. Thank you. Okay. But I'm not asking anybody to recite anything. I'm saying it's written right there. I'm saying what that thing is the definition of the derivative, folks. Like that thing circled in red means the derivative of G, right? It's what I was, and you do, and I do want people to assimilate this over the weekend or whatever you got. Like I was, like the reason we spent or maybe you thought I was asking something harder. Yeah, okay. That may be, I was worried that might be true. I totally, right. You might have all thought I was asking for something even harder than I am. Right. I'm not. So hopefully that was the issue. But it is a big insight. And it's actually why we took pains to like throw in these tangents and all that, because here's the deal. What I'm saying on the left side here is that if we take the G function, evaluate over here minus the G function over there, and divide it all by the change in X, what we're doing is the rise of the G function over the run of the G function, take it to the limit as the run goes to 0. So what I'm saying, what I'm asking wasn't meant to be that hard, but yes, there's a weird thing that's going on here, because what I'm saying is that whole thing circled in red is simply the derivative of G, but G already was the derivative of Y with respect to X. In other words, this whole red thing, so in other words, like I'm saying that whole thing is just the derivative of G with respect to X. But G is a dummy variable. We just made up G right in the middle of this proof. G is not actually anything. What G stood for was the partial derivative of Y with respect to X. So what I'm saying is, if you're following this, then what's tricky or weird about it is this whole thing on the left-hand side is the derivative of the derivative of Y with respect to X. In other words, and I do think this is the hardest insight of the whole proof. Like it's easy once you get it, but it's hard to see until you do. And this is also maybe why you didn't know what I was asking. I'm saying that we have like derivative minus derivative all over delta X. But if we think of each one of those derivatives, like this is actually why we divided both sides by delta X, so we could get it in this form. And it's why it's actually cool and helpful to take it to the limit. The whole left side is really one big derivative, but it's a derivative of something that's already a derivative. And so the whole left side actually becomes, well, there it is. The whole left side is the second partial derivative of Y with respect to X. On the left-hand side, we have a second partial derivative of Y with respect to X. And on the right-hand side, we have a second partial derivative of Y with respect to T. Like this is now suddenly crazy town. I mean, in a good way. And so like this box thing is the result, or you can, traditionally people switch it around and write it the other way. In fact, I'm going to write it again on the next page. So we get that thing on the top. We're literally getting that a second derivative equals some other second derivative. They're both second derivatives of Y, but one is a second derivative of Y with respect to X, and the other is with respect to T. In other words, one is a spatial derivative, and the other is a time derivative. This is definitely the first time this has ever happened to us, because it's the first time we ever had a function dealing with both at the same time. But literally, if I just, if I just rearrange it so I multiply both sides by T and divide both sides by U, I could write it this second way. And that's the way I'm going to tend to write it in this class. So I'm going to write it again right now. I'm just going to write the same thing, but just again, to really make it clear, I'm saying that what we conclude okay, first of all, Okay, it's called the one-dimensional wave equation because this just describes things propagating because it's a one-dimensional medium, because the string is just a one-dimensional line, and yet we're getting these bumps traveling up and down and side to side. Like a lot is going on. There's X, there's Y, there's time, but it's a one-dimensional medium, so it's called the one-dimensional wave equation. This thing is quite a package of information. Like it's really simple, it's really elegant in a way, but you got to know a lot of math and physics to be able to unpack it and understand any of the symbols, right? So let me just make it bigger. Sorry, that's not a mistake. I'm just making it. Okay, what we have here is a second order partial differential equation. It's quite a monster in a way, but it's quite tidy in another way. Like let's compare it to the other differential equation we've ever seen in this class. Like we spent a long time, hopefully for a reason, looking at Hooke's law that we ultimately translated into mathematics. And we said that what Hooke's law ultimately was, the thing in brown at the bottom here, is Hooke's law said that the second derivative of position with respect to time, i.e. acceleration, was equal to a constant times y itself. We said that acceleration was directly proportional to displacement. That's what it meant to be a mass on a spring. We were saying, let me just look at the time. Okay, oh, we have 3 minutes. Perfect. Okay, well, this is it, by the way. I'm just now trying to put this in perspective. But our first differential equation was for simple harmonic oscillation. And the whole idea of simple harmonic oscillation was if at any moment you wanted to know how fast, if at any moment you wanted to know at what rate the mass was accelerating back to its equilibrium position, we found that its acceleration, the rate at which it's accelerating back home, was directly proportional to how far away from home it was. Like d2y, dt, I mean, it could have been x, but I'm calling it y just to make a comparison. Like if you had a vertical spring, it'd be y. So the rate at which the mass on the spring accelerates back home was directly proportional to how far away from home it was. That's the essence of Hooke's law. That's the essence of harmonic oscillation. It was one dimension of space oscillating in one dimension of time. This thing is like the blow up or the expansion of that into higher dimensions. The left side is exactly the same. It says if you want to know the rate at which this chunk of string is accelerating back home, it's going to also be directly proportional to something, but it's not going to be directly proportional to how far away it is from home, because now we're not dealing with a mass that has been displaced along some axis from like in Hooke's law, we had a mass and we had a home position, an equilibrium position, which was just a dot, like a place, and the mass was some distance away from that dot. Here, equilibrium is no longer a dot. It's no longer a zero-dimensional place. Equilibrium is a line. It's the horizontal axis. It's an orientation. So the rate at which some chunk of string accelerates back home to that line is not directly proportional to how far away it is from the line, because that doesn't even make any sense. What would that mean? Like, it doesn't matter where the string is. The string could be up here or up here or up here. It just matters how distorted the string is from that axis, that flat horizontal axis. And one way to note or measure distortion or bump, like, so in other words, this string is going to accelerate, this piece of string is going to accelerate back home at a certain rate, at a rate that is proportional to what we would call in math concavity, right? Remember, in math, the first derivative is slope. The second derivative is called concavity in math. I'm looking at the time. We have like 1 minute. Oh, we have like 0 minutes. You might say, wait, I thought you said the second derivative is called acceleration. The second derivative with respect to time is called acceleration. But the second derivative with respect to space, like when you ever learned calculus in the first place in a math class, when you just look at a y versus x graph, not a y versus t graph, a y versus x graph, y the rate of change of y as a function of x is called slope, and the rate of change of that is called concavity, like how bent, how unflat the function is. So what this says, and this is the last thing I'm saying, and we're done, but very good job, everybody. We're saying here, a wave pulse is like a harmonic oscillation, but in 2 dimensions at once. The rate at which the bump will accelerate back to flatness is directly proportional to how unflat it is at that point, how concave it is at that point. And and this statement must be true at any and every position in the string and at every moment in time. Like if you ever have a situation where this equation is true at every moment in time and in every place, then what you have is a wave pulse. And if you think you're looking at a wave pulse, or you think you have something that have a wave pulse, then you must have a situation that is obeying this equation at every single position in space and every single position in time. This is the wave equation. We are done. You've been very, very good. If I can get a goodbye, there's no new homework or anything like that. Thank you for being so patient. If I could just get a goodbye, then I will say goodbye and have a great weekend. Thank you. Okay, great. Thank you. Great. Thank you. Awesome. Goodbye. Thank you. Oh, nice. Thank you. I appreciate that. I totally do. Really, more ways than one. All right. Thank you. Cool. Goodbye. 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 I'm looking for notes and blah blah blah. Thank you very much. Awesome. Thank you. Okay. Awesome. Awesome. Blah 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 blah. Blah. Where's the end? Okay. Awesome.